All right, silly people, here's the situation. We have a perturbation on the Hamiltonian for the simple harmonic oscillator equal to lambda x to the fourth. And we are meant to calculate the first order corrections to the energy eigenstates, um, or energy eigenvalues, actually, um, due to this perturbation in the harmonic oscillator. So for us, uh, that means that we're going to have in here psi n star lambda x fourth psi n dx, where psi n are just the solutions to the unperturbed harmonic oscillator, and that's the first order corrections. So um, I'm going to factor out a lambda from the integral, and I'm also going to actually use a identity specific to the harmonic oscillator where you can replace the position operator with h bar over 2m omega times the sum of the raising and lowering operators. Um, so with that in mind, you'll have an h bar over 2m omega squared there. And then in the integral, you have psi n star a plus a dagger squared psi n dx. And it's not squared, actually, it's raised to the fourth power. And if there's a part of this problem to mess up on, it's the expansion of that polynomial of operators, so I'm going to do it exceedingly carefully, I think. So expanding to second order, it's going to be a squared plus a dagger plus a dagger a plus a dagger squared psi n dx. And then we're going to square that thing in there. You'll get a bunch of terms that are going to be a to the fourth plus a cubed a dagger plus a squared a dagger a plus a squared a dagger squared plus a dagger a squared plus a dagger a dagger plus a dagger squared a plus a dagger cubed plus a dagger a cubed plus a dagger a squared a dagger plus a dagger a dagger a plus a dagger a dagger squared plus a dagger squared a squared plus a dagger squared a dagger plus a dagger cubed a plus a dagger to the fourth times psi n dx. So yeah, we have a lot of terms, but I'm going to go ahead and cancel out a bunch of the terms which depend on factors of a and a dagger that aren't equal. So I'm throwing away this thing and this thing and this thing. This one actually has an equal number of raising and lowering operators, so I'm going to keep that one, but throw away this one, keep this, keep that, throw away that, throw away that, keep, toss, keep, toss, toss, toss. So at the end, I think we should only have 6 terms, so 6 integrals that we need to calculate. So we have an integral psi n star a squared a dagger psi n dx, and that's a dagger squared, plus integral psi n star a dagger a dagger psi n dx plus integral psi n star a dagger squared a psi n dx plus integral psi n star a dagger, or nope, just a dagger a squared a dagger psi n dx plus integral psi n star a dagger a psi n dx plus the integral of psi n star a dagger squared a squared psi n dx from minus infinity to infinity. So I'm only going to really apply operators one at a time so that I don't confuse anybody. And so first one will be root n psi n star a squared a dagger root n minus 1, or psi n minus 1 dx plus integral psi n star, and actually apply the operator. So it's a lowering operator, you'll get root n. Psi n star a dagger a root n minus 1 dx plus, and then it's a raising operator, so it's a root n plus 1 times integral psi n star a dagger squared psi n plus 1 dx plus lowering operator, so root n psi n star a dagger a squared psi n minus 1 dx. And then raising operator, so root n plus 1 psi n star a dagger psi n plus 1 dx plus integral, and actually do the operator, so it's a raising operator, so you'll get root n plus 1 integral psi n star a dagger squared a psi n dx minus infinity to infinity. So just chugging along here, applying the next set of operators. Now we'll have a factor of root n times n again. No, it's n minus 1 actually, because it's a lowering operator. So psi n star a squared psi n minus 2 dx. But this is going to be overall factor of n now. Psi n star a dagger psi n dx plus, now we have a lowering operator, so it's an overall factor of n plus 1 integral psi n star a dagger psi n plus 2 dx. And not n plus 2, it's just n now. Yeah. Psi n dx plus, it's a raising operator, so an overall factor of n times psi n star a dagger a psi n dx plus, it's a lowering operator, so an overall factor of n plus 1 integral psi n star a dagger a psi n dx, and then it's another raising operator, so it'll be n plus 1 times n plus 2 integral psi n star a dagger squared psi n dx. And I'm just going to look and see if I can collect any terms. I actually can collect terms. That's pretty cool, because this term matches this one and this term matches this one. So before I apply any more operators, let me just collect those terms together. we'll have n and minus 1 there. Can't really do anything with this yet. And then you'll have 2n plus 1. Yeah, 2n plus 1 times integral psi n star a dagger psi n dx. And then also a couple of a dagger a terms, which also adds up to 2n plus 1. Integral psi n star a dagger a psi n dx. And then also the last term, which is this thing. And we're going to apply the next round of operations now. So that's going to be a raising operator. So you'll get n times, or root n times n minus 1 psi n star a psi n minus 1 dx plus 2n plus 1 times root n integral psi n star a psi n minus 1 dx plus 2n plus 1, now featuring factor of root n plus 1, integral of psi n star a dagger psi n dx plus a lowering operator. Really? I think I made an error here, and this is supposed to be yeah, definitely. So this is supposed to be n plus 1 dx minus infinity to infinity. It doesn't change much, it's just now actually writing things out properly. This will be n plus 2. This will be n plus 2 here as well. Yep. Okay, now I have a lowering operator, which will give us an additional factor of square root n plus 2. So just there, and then integral psi n star a dagger psi n plus 1, all from minus infinity to infinity. And apply your dx's where appropriate. And then we can do another simplification now, because we have a couple of integrals that are grouped like root n times the integral psi n star a psi n minus 1. Those add up like 2, it's 3n. Yeah, it's just 3n. So 3n psi n star a psi n minus 1 dx. And then another couple of factors which both depend on root n plus 1, which add up like 3n plus 3. Integral psi n star a dagger psi n plus 1, it's supposed to be plus 1 there, dx from minus infinity to infinity. So finally, we can do our last round of operations. You'll get a factor of 3n squared integral psi n star psi n dx plus a factor of n plus 1 times 3n plus 3, integral psi n star psi n dx from minus infinity to infinity. And both of those integrals are 1 now. So we will just expand the n terms. So we'll have 3n squared plus another 3n squared plus 3n plus another 3n plus 3, which will add up like 4m squared omega squared, 6n squared plus 6n plus 3, and we can factor out a 3 to have 3h bar squared lambda over 4m squared omega squared, 2n squared plus 2n plus 1, which is what Shankar was trying to get us towards anyway. The question then asks, after that, a couple of questions that don't really have any calculations to them. It says, argue that no matter how small lambda is, the perturbation expansion will break down for some large enough n. And that's not too hard to see with your eyeballs, because in the limit where n goes to infinity, our first order corrections will kind of go like 3h bar squared lambda times 2n squared over 4m squared omega squared, which when you simplify that looks a lot like not like the energy eigenvalues for the harmonic oscillator anymore, but now more like the ones for a particle in a box or a free particle, which, I mean, yeah, it falls apart. It looks more like a particle in a box rather than a free particle. Physically, I think that has to do with the fact that x to the fourth is just a ridiculous field to apply to a particle, a bunch of particles, and still call it a harmonic oscillator. There's just, when it gets to too many particles, you now just have a bunch of particles flying around with periodic boundary conditions, and the potential isn't really helping matters that much, so it just becomes like a soup of particles which has those energy eigenvalues instead. So yeah, that's my best take on it.